So this is the beginning of chapter 3, which is on the roots, soil, and uptake of nutrients. It concentrates heavily on mineral nutrients and how plants take up those. So we'll be looking at how nutrients move through the soil, how nutrients move into the root, different kinds of uptake, and then we'll be moving into some discussion about nutrient deficiencies, and also how nutrients cycle in the soil and within plants and soil. So we'll start with just kind of a basic, quick review of what we know about soil components, the components of the soil so far. So we talked about this with the last chapter. So remember, there is a solid phase, which includes different sized particles that result from weathering of parent material or bedrock, and that those particles have varying sizes that's displayed over here, this diagram that we've seen before, with sand being the largest, then silt being the next diameter particle, and finally clay being the smallest. Now clay is what we're primarily going to concentrate on in this discussion for the mineral soil. Remember, this is the mineral soil components. All right, the second part of the solid phase includes organic materials or organic matter. And remember, organic matter comes from previously living materials, whether we're talking about plant materials, animal, different kinds of bacteria, fungi, whatever previously was living contributes to the organic matter in the soil. And this organic matter decomposes. So organic matter decomposition, and into a form of unrecognizable organic matter, which is called humus. So remember, that's unrecognizable organic matter. No longer can recognize it as a leaf, in other words. The second component, large component here of the soil is the liquid phase, or what we call the soil solution. And the soil solution consists of water plus dissolved nutrients, and those nutrients can be different kinds of ions, organic acids, whatever can be dissolved in the soil, sugars even. The soil solution is a rather dilute solution, on the order of something like, just as a target here, of 1 molar concentration of whatever we're talking about, or the sum of all solutes. And our third phase here is the gas phase. The soil solution is the liquid phase. And the gas phase, remember, is anything that we would normally find in the atmosphere: oxygen gas, nitrogen gas, carbon dioxide gas, and it's always in equilibrium with the atmosphere. Okay. Then we have our soil community, and we'll mention those a bit more this time, which are basically all the other living organisms in the soil, such as earthworms and bacteria and fungi and invertebrate organisms, and they basically set up a whole food web of interactions in the soil. And as a result of their activity, they lead to decomposition of organic matter. And basically make nutrients available to the plant, in part. We'll see a couple of different sources of nutrient availability for plants, but this is one of them. All right. So that brings us to the next figure here, which shows us interactions, all kinds of interactions between the root, the plant itself, the shoot itself. As the shoot becomes organic matter, or the roots become organic matter, they decompose, bringing in nutrients. Weathering is another source of nutrients that basically weathering being chemical weathering, where ions are freed from the parent material. So we're going to kind of take a look at what's happening in the center of this figure here. So what we're looking at right in this area here that we're going to outline in blue is the soil colloidal complex. So we're looking at soil colloids here. And these colloids are formed. They're sort of like a unit of soil structure. So they're formed by the combination of clay plus humus. And basically, as we remember, the clay has a very small diameter structure, and humus can too, actually. So because of that, each of them have a high surface area to mass or volume ratio. And so the question is, what are the benefits of that? What is the benefit of having a high surface area to mass or high surface area to volume ratio in the soil? Okay, the benefits of a high, and I'm abbreviating here, surface area to mass or volume ratio is that it maximizes the adhesion of ions to the colloids. Okay, so if we take a look over here at the colloids, we see that there's a lot of positively charged ions that are attracted, and that's because the soil colloidal complex is full of negative charges on the surface here. So what brings those negative charges is that clay is basically formed from aluminum silicates in many of the clays that we see. So when these ionize, they they form negative charges. And that's what brings these negative charges on the surface. And humus is a combination of organic materials like lignin and other carbohydrates, along with all kinds of other organic acids. I'll write that down. Organic acids like tannic acids, and there's just a large number of things that we could include here. But as a result, because these are organic, there's a large number of hydroxyl ions with the negative charge, as well as carboxyl ions with the negative charge. And so those negative charged parts are going to also attract these positively charged ions. So the colloids have negative charges, or they're negatively charged, and therefore attract cations, positively charged ions such as potassium and magnesium and calcium and ammonium and sodium. And you can look over here at a long list of different kinds of cations, even iron and manganese, and all kinds of things that we could list. Okay, so that means So the soil's binding to these cations serves as kind of a nice stable place for these cations to remain in the soil so that they don't get leached out or washed away by the soil solution. So we would say that the soil colloids are the primary nutrient reserve for plants. They're that longer term storage compared to being in the soil solution. So colloids are the primary nutrient reserve. Okay. So that brings us to the next question, which is basically we want to know how tightly are the cations bound to these colloids. And that is going to vary based on the kind of ion we're looking at. How tightly are cations bound to colloids? Right, so binding affinity is going to vary from ion to ion, or basically varies based on the valence of an ion. So trivalent ions are held more tightly than divalent ions, which are held more tightly than univalent ions. And so what we can create here is then a binding affinity series. So the binding affinity series goes such that here we have aluminum with which is a trivalent ion. It has a higher binding affinity, so this is the high binding affinity end of the series. High binding affinity. It has a higher binding affinity than hydrogen ions, which is one of these other kinds of ions that's we'll have to talk about a little bit more since it affects pH, and it interacts with negatively charged ions in such a way to either increase or decrease pH. It has a different sort of effect here, but anyway, it has a high binding affinity. But then we go back to our valence series here, which the next highly binding affinity ion is calcium, which binds more tightly than magnesium, which then binds more tightly than now our monovalent ion potassium. And that binds very similarly to ammonium, which is greater than or more tightly held than sodium. So that means that in this binding affinity series, we have to also know that we are assuming that all ion concentrations, that's an abbreviation for concentrations, is equal. So we have to assume equal ion concentrations to use that binding affinity series. So what that means is, say, for example, if we have, if say calcium ions are in solution, in the soil solution, then they exchange, I'm abbreviating heavily here, exchange with something lower in the binding affinity series, assuming the concentrations are equal, such as here, ammonium, which is a plus. We can also assume either basically that the ions or concentrations are the same, or that lower binding affinity ions are less than higher binding affinity ions in concentration. Okay, so then that series would still apply. Alright, so actually there's a little error here in our series. We want to get rid of that too. It's just a positive 1 on the sodium. There we go. We can also assume higher exchangeability at the low end, where these ions are going to exchange more readily off the colloids than something that's more tightly bound. So we can say that exchangeability of ions runs the reverse of the binding affinity series. Binding affinity series.